All right, here we go, 9.2. In 9.2, we're going to talk about discontinuity. Okay, we're going to recognize discontinuities from our graphs and find holes in vertical asymptotes of a function. Okay, we'll do that algebraically and by looking at an actual graph itself. All right, and or our table, either one. Here are some definitions that we're going to talk about today. Okay, but I'll just jump right to the first one: discontinuity. Okay, discontinuity is where a function is not continuous and the value of the function is undefined. So if you think about discontinuity, okay, I think about not continuous. What does that mean? Not continuous means if my pencil is over a function, all right, I don't actually want to draw on there, sorry. If I'm dragging my pencil over a function, okay, and while I'm dragging over that function, I have to pick up my pencil to get to the next part. Okay, if there's a jump, maybe there's a jump, maybe there's a break in our function, maybe there's an asymptote. That's when a discontinuity happens. Okay, you think about where the function is undefined. Well, that's going to include our domain. Okay, so in this graph down here, I'm going to draw something. I'm going to ask you to mimic it, and I will, or draw it as well, and I'll explain it in a minute here, what it all means. Okay. All right. So, you can pause. Don't worry, you can pause. Right here. What is this? This right here is called a jump. When there's a hole at one part and a closed dot another part. These jumps normally occur when we're dealing with piecewise functions. Okay, we've talked about piecewise in the past, or you probably have at some point, maybe in this class, maybe not, who knows, maybe you know, maybe I should know, maybe that's right. Yes, we've talked about piecewise functions in the past, okay, and we're not really going to focus on jumps a whole lot this semester, okay, or for now in this unit, but you will at some point. Okay, so that is what that jump happens when we're talking about piecewise functions usually. This line right here, we talked about in the last video. This is our vertical asymptote. Okay, our vertical asymptote is a vertical line, therefore it's always going to have the equation x equals. For this particular x equals some number, in this case it's going to be -1. Okay. This right here is called a hole. All right, a hole at, and this is how we're going to write it, x equals 1 with a value of 1, 1, which means like, hey, if this value did exist, if the function did exist at this x value, then I would have the 1 as my output. However, there's a hole there, meaning we do not include this. Okay, do not include this point. All right, x cannot equal 1, therefore there's that hole there. There's a gap, and a hole happens. It's a value at which the denominator of a rational function is equal to 0, but it cancels out with the factor in the numerator. So what I want you to do is I want you to, oh buckets, what's going on? I want you to graph this function f of x equals x squared minus x over x minus 1. I want you to do that in your graphing calculator. You're going to need your graphing calculator for this video. I should have said at the beginning. My fault. I apologize. You're going to need this graphing calculator for the video. Okay. But I would put this, make sure you use parentheses here and here. I do not have the sick like graphing calculator application on this computer, so I'm going to show you the Desmos version. Okay. This is what your y equals should look like. All right, with parentheses using the division. If you look at this graph here, you recognize that it looks very similar to our function, sorry, y equals x. All right, y equals x. But there's something that you're going to notice, all right, by looking at our table. So what I want you to do is go to your table, all right, go to your table, and you'll see at 1, at x equals 1, you'll have this error. It's at x equals 1 here, all right, my at x equals 1, my function is undefined. There's an error. That means I'm going to have a hole at x equals 1. Well, how could I find that out? Well, as it says here, if I were to factor x minus 1 over x minus 1, you'll recognize that our x minus 1s cancel out. Okay, so there's a hole at x equals 1. Well, at x equals 1, there's this hole. That's how we would graph that. And the function goes on forever that way, and it goes on forever this way. A hole at x equals 1, and it's 1, comma 1. All right. If you think about this here, it's what's our domain? Our domain we think about first, all real numbers except x what? X cannot equal 1. Well, there's also this hole. There's this error, okay, at x equals 1. All right. As we continue to do more, this will make more and more sense. Okay. I'm not going to have you plug this in. Let's just think about it algebraically now. All right. The first thing I want to do is factor. First thing we should do is factor. All right. So I factor out my denominator. I get x plus 5, x plus 2. Well, some of my factors cancel. Excuse me, not some, but one of my factors cancels. So this factor cancels out. So I'm going to have a hole at x equals 2. Now remember, even though this cancels out, we still pretend like there's this 1 that exists there. All right, so I want to think about if I were to input, I want to input 2 into my x value. Now, after I cancel out the hole, input 2 in here, I would have 1, excuse me, that should be a 2. I would have 1 divided by, that should be a negative 2. Negative 2 plus 5 to give me 3. Okay. 1 over, that's a negative 2 plus 5 to give me 3 on the denominator right here. And that's a negative 2, I said, right? Negative 2. Well, let's also talk about, while we're here, let's talk about a vertical asymptote. Okay, remember a vertical asymptote happens at a value which the denominator of a rational function is equal to 0, and it will not cancel with a factor in the numerator. So we think about this here. All right, well, what is still causing us problems in our denominator? This x plus 5. Okay, granted, the x plus 2 did as well, but it cancels out with a factor in the numerator. But this x plus 5 is causing us problems, and it doesn't cancel with anything up there. So in this rational, excuse me, for this rational function here, I'm going to have a vertical asymptote at, well, the x plus 5 is causing me issues, so I'm going to have a vertical asymptote at x equals negative 5. Okay, we're going to determine our vertical asymptotes by what's left over. All right, by what's left over. That's why there wasn't a vertical asymptote here at x equals 1, because there was the hole at x equals 1. Okay, what I want you to do here, all right, I want you to pause this video. I'd like this to be in your, put this into your calculator. All right, so I'm going to plug this in like I did here into my y equals. I'm not going to show you that graph. Oh boy. All right, plug this into your y equals. Make sure you have parentheses in the numerator, parentheses in the denominator, just like I have here. All right, and graph it up. And I want you to use this window, use these window numbers for your window, and try to answer these 3 questions. Go. All right, so here's what I got in my answers. I drew a rough little sketch here. Okay, to find out our hole, again, I want to factor and factor. Okay, if you'll notice that the x plus 4's canceled out, but I'm still left over with the 1 over x minus 1. Well, this x minus 1 is causing me a problem. There's my vertical asymptote is here. You can see that by looking at the graph as well. All right, my line approaches 1 but never crosses it. Okay. Since I canceled out x plus 4, that means I'm going to have a hole at x equals negative 4. Input that negative 4 into what's left over. So right here. All right. I get negative 4 comma negative 1/5. That could be negative 1 over 5 or 1 over negative 5. It means the same thing. Okay. All right, find the holes in vertical asymptotes. That's all we're going to be doing on these next 4. Okay, so the first thing I want to do is factor x plus 4, x minus 4. Factor the denominator, x plus 4, x minus 3. Okay, so what cancels? The x plus 4. Whole. Hot. Whole. Whole. At x equals negative 4. Value. Negative 4 minus 4 is going to be negative 8. Negative 8 over negative 4 minus 3 over negative 7. So 8 over 7. Two negatives make it a positive. Vertical asymptote. What's still causing me a problem in my denominator? Oh, it's this x minus 3. So I have a vertical asymptote at x equals 3. Wow. Weird, wild stuff. Let's keep going. I'm having too much fun. First thing I want to do, factor 2x squared, GCF, x over x plus 1. Cancel x's, and one of the x's cancels out up here. So that tells me I have a whole at, what is this? X equals 0. Plug in 0. 2 times 0 is 0. 0 plus 1 is 1. 0 over any number is just 0. Vertical asymptote. What is still causing me a problem? Oh, it's this x plus 1. That factor there, x plus 1. So I have a vertical asymptote at x equals negative 1. Okay. I'm going to do a recap at the end. First thing I need to do, factor x plus 3, x minus 2 over x times x squared plus 2. Does anything cancel? No. Holes. You can have no holes. That's a beautiful thing. Vertical asymptote. Well, I got this issue here, so x equals 0. All right. And I want to set this equal to 0 as well. X squared plus 2 cannot equal 0. X squared cannot equal negative 2. Root x cannot equal plus or minus I radical 2. Since this is an imaginary number, okay, we're not going to graph imaginary numbers, so I can toss this one out. So this will not really cause me issues in my denominator or in my function, only that there. Okay, so you do not have to include this over here. All right. I did this anyway just to make sure that I didn't have to include it, just to make sure that it was an imaginary root. All right. Here we go. Let's do this. Let's do this one. Holes, negative 4. Factor first or simplify. I could have this x minus 2. Since it's cubed, it's going to happen 3 times. Is there anything that factors? No. Or excuse me, that cancels. Nothing. Vertical asymptote. Well, there's a lot going on. All right, I have a lot of denominators that I have an issue with. Well, fortunately for me, I only have to include one of them. There's only going to be a whole at x equals 2. It may happen 3 times, but it's at the same exact number. All right. So what's your process for thinking about this unit? All right. The first thing I want to do when I'm dealing with a rational function, I'm asked to find the holes in vertical asymptotes. Okay. I want to factor. Factor the numerator, factor the denominator. Okay. As I'm factoring, I want to think about the domain and range, or think about the domain as it pertains to the denominator. All right, think about your domain. So first thing is factor. Second thing is think about the domain. Third is cancel any factors if you can and find your holes. All right, and find your holes. The fourth thing you want to do, look at your leftovers. All right, look at your denominator, see if there's still any problems, and then write your vertical asymptotes. So that's factor, think about your domain, cancel, look for any more issues in your denominator for your vertical asymptotes. All right.